Volvo Construction Equipment is a leading manufacturer of heavy-duty machinery such as trucks, wheel loaders, and excavators. At the core of these machines lies a critical component, the gearbox that ensures smooth power transmission. Like any mechanical system, gearboxes can develop faults over time. Therefore, regular testing and fault detection are essential to keep them in good shape. Urina is a testing operator at Volvo Construction Equipment. Every day she starts the gearboxes and listens to them. She has carefully listened to the sounds of every gear one by one. However, this process eventually tires her, she gets burned out, and her judgment naturally becomes impaired. As a result, the testing process becomes unreliable and her satisfaction with her work diminishes. Apparently, an AI solution is needed to automatize this process.
Edis Intake 3 developed an AI-based model that could analyze the gearbox testing audio and could tell whether a gearbox is faulty or not, making a big step forward in automation. However, it couldn't tell whether their issue lies in a specific gear or not, which makes further manual checks necessary. Our solution takes fault detection further by identifying the actual gear causing the issue. Each gearbox consists of 6 gears, 4 forward gears, F1 to F4, 1 neutral gear and 1 reverse gear. During testing, these gears are sequentially activated. Using our fragmentation algorithm, we split the gearbox audio into 6 gearbox separate audio files. Instead of training our entire gearboxes, our model learns from individual gears, allowing the model to precisely identify which gear is faulty and to what degree.
Now, to understand our solution better, let's take a look at the pipeline. We start with data pre-processing. We have around 14,000 normal and 81 anomalous gearbox audio samples. We keep only those having the duration between 40 and 60 seconds. The next stage is augmentation. Since we have too little anomalous data, we artificially generate more for better testing. Later, we fragment the gearbox into individual gear sounds. As features, we use logMAL spectrograms that capture time and frequency patterns, making them useful for detecting machine faults. They are created by applying short-term Fourier transformation, converting to the MEL scale, and using a logarithm to highlight small variation. The features are later used to build an anomaly detector using an autoencoder. The autoencoder is trained on normal samples only, so it knows how to regenerate normal samples better. When it regenerates a sample poorly, it means that the original sample was a faulty one. Finally, using an anomalous scoring formula, we score our predictions.
Training our autoencoder was just the first step, but testing was equally crucial. We needed to see how well the model could predict fault. We only had 80 faulty gearbox samples, which was far too low for robust testing. To address this challenge, we turned to data augmentation. We applied manual techniques like white noise injection, time stretching, and pitch shifting, expanding the faulty dataset to around 800 samples.
Now, let's take a closer look at the preliminary results we obtained from testing our model. For training, we used around 5,000 normal gear fragments, while for testing we had 750 fragments that included both normal and faulty samples. From the confusion matrix, our model achieved an accuracy of 90%. Precision is 95%, which means that when the model predicts a gear is faulty, it's correct 95% of the time. The most important metric, recall, is 71%. This is crucial because misclassifying a faulty gear as normal is riskier than the other way around.
Now that we have a model, Urina can test the gearboxes just in a few clicks. It might be a small step in her work. However, in a broader perspective, using the AI techniques for quality control of machine parts has the potential to revolutionize the construction industry.
I think it's fine.
Go, say something.
Okay, so this is a trial shot and I'm just